Hey everyone, my name is Jerry. Welcome back to another episode of the LlamaIndex webinar series. Today we're joined by Omar and Thomas from the DSPy project. And the title of the slides are Compiling Declarative Language Model Calls into Self-Improving Pipelines. It's a cool framework that has been under development for a few months now, and there's a lot of new concepts in there that you don't really find in other frameworks, especially the stuff around like auto optimization of the pipeline through the compiler, as well as like removing the need for prompt engineering and the importance of few-shot examples. So I'm personally super excited to learn a little bit more about this. And so we'll do about like 25 minutes of Q&A, or not Q&A, slides. And then we'll do about like 25 minutes of Q&A. So if you guys have any questions, please feel free to drop it in the chat. And then I'll probably ask some questions as well towards the end. Cool. Without further ado, passing it over to Omar and Thomas.
Perfect. Okay. Well, thank you so much, everyone. Thank you for coming out today. Thank you so much to Omar, Khattab, the creator and leader of DSP, the advisors, Chris Potts and Matej Zaharia, and thank you to the wonderful DSP team. What I'll be doing at first is just kind of setting up the LM ecosystem at large so that Omar can then introduce DSP and how it solves those challenges. So, one of the most common questions we get is, where does DSP fit into the landscape of tools? So let's zoom out. We have all these emerging theories and techniques on how to improve LLMs. You have adaptation, which includes different prompting techniques like few-shot, where we enable in-context learning, where we provide demonstrations in the prompt to steer the model. You have reasoning, so it includes chain of thought, where we enable complex reasoning capabilities through intermediate reasoning steps. You have augmentation, so that's including providing the LLM information, which is a piece of text that could generate the correct or useful response. And there's also specific designs into how you can retrieve this information. Now, obviously, we're preferential to Omar's Colbert model, but obviously there's a lot of different other retrieval methodologies. And so DSP really focuses on coordinating your language model and your retrieval model. So we first translate string-based prompting techniques, including complex and task-dependent ones like chain of thought, and React into declarative modules that carry natural language type signatures. So currently, these tasks are solved using domain-specific pipelines. So some examples of this are flares. So the study introduced flares. It's a retrieval augmented generation method that actively determines when and what to retrieve during text generation, using predicted upcoming content as a query to gather relevant information. And you have SQL and offers a blend of hand-prompted LLMs combined with a SQL database for Texas SQL. You have the RAR system that automatically provides attribution for language model outputs and corrects unsupported content, enhancing kind of the trustworthiness of the system. And each of these pipelines exemplifies dedication to task-specific design, which exchange flexibility with performance. And so if you're an engineer building out these pipelines, or you're a researcher, you want to set up yourself up for success later down the road in case something changes with your foundation model, your retrieval model, user behavior, etc. So while pipelines offer great potential, crafting them effectively is quite challenging. Firstly, figuring out how to seamlessly connect and optimize every element of a pipeline can be elusive. Moreover, prompts used in these pipelines can be very delicate and don't easily adapt across different scenarios. And if that wasn't enough, fine-tuning them can be an intricate process, adding another layer of complexity. So as you can see, while pipelines that are really tailored to a specific problem are promising, they come with their own hurdles. So this screenshot is from DIN-SQL for a paper for converting natural language to SQL. And you can see these massive handwritten prompts. And right now, many NLP researchers are writing demonstrations and often these long free-form prompts by hand. So it's a good way to kind of give yourself a nice chuckle is to read from really brilliant paper, the React paper, looking at kind of the prompt, and it's sort of an extensive prompt that we don't need to go into today. But the point is that currently researchers are kind of getting around these issues, trying to leverage the power of large language models by creating these really long-winded textual prompts. And with that, Omar, please take it away.
Thank you, Thomas. Let me set up my screen sharing as well. All right, cool. So I guess this is time to introduce you to the DSPy paradigm and how we tackle the challenges of prompt engineering these days. And our main sort of statement is that we'd like you to program and not prompt language models. So our goal is to help you shift focus from tweaking the language model or hacking on prompts to focusing on good architecture design for your system. So the kinds of pipelines that Thomas was introducing. And we do this by basically bringing in three key concepts. So these are signatures, and we'll discuss this in a little bit. These are going to abstract the role of prompts and also a fine-tuned language model weights. Basically, whatever you condition the language model on in order to teach it a subtask in your pipeline. The second sort of class of concepts we introduce is that of modules, signature-based modules in particular. And these will generalize all the prompting techniques you see coming out in the literature and will allow them to be sort of naturally composed into multi-stage systems. And the key thing about modules is that these will be internally parameterized such that they can learn from data. And we'll see what that means exactly in a little bit. The third concept we introduced is that of teleprompters. So these are optimizers for your entire program that will essentially look at your data and your modules and will push the behavior of the system incrementally or iteratively towards any arbitrary metric you'd like to optimize for. So to sort of make this more concrete, things like chain of thought, React agents, and other sort of advanced things there, like program of thought, other things you've heard of. These in DSPy are modules that you can build pretty easily, and the ones listed here are things we have built in. And what these are going to do is that you are going to declare them with a signature. So a signature is simply going to say, I'd like this module, could be any of these, to essentially exhibit the behavior, the input-output behavior that semantically matches those roles. So for example, you could have a chain of thought element that takes questions in and generates answers. And instead of sort of thinking about how you would condition a language model on a long prompt or few shot examples or very specific instructions in order to do that, or how you can find a fine-tuned model or maybe construct it yourself to do that, you're simply going to say, I'd like the behavior of taking in a question and outputting an answer to be sort of assigned to a chain of thought module that I'll then use in my system. And then I'm going to rely on DSPy's compiler, in particular, a specific teleprompter, like one of those at the bottom here, which will take my system, sort of take the context it's working in, so maybe your data and whatnot, and is going to work to optimize these components towards notions of self-improvement. So let's kind of see this concretely. But before that, if you're familiar with neural networks, you can easily sort of assume anything is the way it would be in PyTorch if the language model was your device. And 9 times out of 10, by design, your guesses will be right. And this is sort of one of the reasons I think people pick up DSPy pretty quickly. So if you're familiar with neural networks, that's going to help. If not, it's not an issue. But you can basically think of modules in DSPy as your layers. In something like PyTorch, you might have layers like linear layers or convolution layers, dropout, and other sort of transformations. These are exactly what modules here are going to play the role of, but they're instead working at the level of a high level of transformations that the language model is conducting. Signatures are essentially simply specifying the kind of the function behavior, the input-output behavior of a module. So in PyTorch, this might be like the dimension of your, layer or the number of channels and whatnot. And teleprompters are simply optimizers. So, Adam, SGD are popular ones there. Here, we'd have things that bootstrap few shot examples or optimize with, hyperparameter optimizers and whatnot. So let's get concrete. Let's say you want to solve, I don't know, a math word problem. You could do all kinds of things in DSPy, things that use retrieval and things that don't. So maybe you want to work with this GSM8K dataset, pretty popular in the literature. So it has questions like this, math word problems, and the answer is a number. And it's usually of the sort that requires at least a little bit of bookkeeping. It's not intuitively a number you can immediately extract from the answer, but they're grade school math, so it's not too advanced or anything. So you might say, I'd like to have a system that could solve these kinds of questions. And, it's a fairly arbitrary task. You could plug in something else here. So your first attempt at this, you're starting, in a clean, systematic kind of engineering style. So you're starting simple. So you say, maybe I want to build a module that's going to take the question, go to the language model, simply interact with it once, and ask it to commit to an answer. So the way this would look in DSPy is that you can define a module called vanilla. And all this is going to do is it's going to instantiate the DSPy.predict module, and it's going to tell it the signature we want. So I would like it to take a question and give me an answer. And then you can test this, but maybe we can come up with more interesting designs. So a different design we could have is to basically say, I'd like a system that can do a chain of thought. So I'd like it to, think step by step before it commits to an answer. And in DSPy, this is also built in. So you could just say, I'd like a chain of thought that can take a question and output an answer. Notice that the role of the signature here is important. If you are to replace, for example, question and make this search query, it's going to generate search queries for you. So it's basically working on interpreting, the semantic elements of the signature to determine the behavior that you're trying to describe. So this is 2023 and it's October, in fact. So maybe you'd like to build something more sophisticated. Maybe you'd like your system to do chain of thought given the question, but maybe it should not commit to one answer. Maybe it should sort of prototype 3 different answers. And given that, you could take a majority vote, but maybe you could do something more sophisticated. Maybe you could ask the model to look at all 3 rationales and their answers and essentially compare them before committing to a final answer with another chain of thought. So in DSPy, it would be this block of code. And what I want to emphasize is that in each of these 3 programs, this is the entire specification of the program. There are no prompts anywhere. We didn't write the prompts for this internally. You're not going to write the prompts for this internally. This is the complete specification of your behavior. So let's go through this step by step. What we are going to do is we're going to define a class in Python. This is very similar to the way you would define a neural network in PyTorch, by the way. And you're basically going to say this is a DSPy module. With that, you're going to define 2 key methods. The first is initialization. So here you're simply going to declare the components of the module that you are interested in. So these are basically the boxes that we have. So we'd like to have a chain of thought component that's going to take a question and output an answer. And this is sort of the general behavior that we are going to expect from it. But we also want it to output multiple things. So we can give it, the number of outputs. Another component here, or another module, is the multi-chain comparison. And ultimately, it's still working in the space where, we have an input question that it wants to answer. But it also can take sort of these intermediate things by design. And so it will take, whatever number of attempts is. The second element that you define is your forward function. And this is sort of inspired by the way things work in PyTorch, where you can basically write any code you like. We're not going to give you weird sort of handicapping abstractions for chains. Just write Python code. You could have loops, you could have exceptions, you could have, you could call other functions, you could do whatever you want. Just make sure you use these modules that you declared in the places where you want to interact with the language model. And with that, you can just instantiate it by saying, I'd like a version with 3 attempts. And this is simply going to declare the architecture you have in the right hand. Notice that here we didn't say, I'd like this to use OpenAI models, or I'd like this to do prompting, or I'd like this to do fine tuning. All of these are low-level details that can be figured out after you've designed your network, and in many cases can be figured out pretty effectively in an automatic way. So let's actually kind of work on compiling one of these. So once you build a network or a program in DSPy, what you do is you compile it. This is kind of like training a model, but when working with these programs that interact with language models. So the general signature, or the general sort of interface to a compiler, is that there is this teleprompter that you pick. So there's this optimizer. You give it your DSPy program, and you give it some number of examples, generally with very sparse labels. So you could have a small number of examples, many of them without any labels, and maybe a few labels on the final output that you expect from your system. Depends on your metric, really. And generally also admits a lot of unlabeled examples, depending on your use case. So you give it your program and a few examples, and you select a specific teleprompter. So we have a lot of these for different kind of applications. They're all general purpose, though, so you could use any of them. And what you get out of that is sort of a specific implementation of your DSPy program that's generally optimized for whatever metric you'd like to target, generally along axis of quality or cost. So we just defined 3 programs, and I promised you that this was the entire definition of these programs. Now we need to actually be able to execute them. So we could take our chain of thought program, or really any of them, and we need a training set of examples. So maybe we have some of these questions and their answers. And notice that our answers here are simply going to be numbers. No one is going to bother to write annotations for sort of all of the intermediate stages of our pipeline. So in particular, we're not writing a chain of thought by hand, because like, how do you do that well for the model? You don't know what exactly, what works for it. What works for Llama is not what works for GPT 3.5 and whatnot. So you write your training set, could be a handful of examples, could be large also if you want to if you have a lot of data and you want to optimize sort of more aggressively. You declare your module, essentially your program, you pick a metric and you simply ask it to compile. And what you get out of that is a bootstrap program where every module, in this case, there's only one module, but where every module has sort of been mapped into an implementation in accordance with the teleprompter that you have. So here, this is a bootstrap few shot teleprompter. So what this is going to do is it's going to work on few shot prompting. So under the hood, if you're working with Llama 213 billion chat, it self bootstraps to this set of chains of thought. And there's a bunch of other demonstrations here skipped for space. But internally, it's able to sort of find or really create this prompt that works really well under the hood, and we'll see how that works in a little bit. So there's a lot of other teleprompters. If you have labels that you'd like to use, you could use a labeled few shot teleprompter. You can bring your own labels if you have them. Not generally the way we like to do things, but you could ask the model to sort of bootstrap or sort of kind of self-create and potentially iteratively improve few shot examples with random search. You could do it also with kind of fancier search algorithms. We have support for Optuna. You could also nest these things. So you could bootstrap based on the bootstrap program. And this is kind of an interesting form of distillation where you're not distilling a model to another, but you're distilling a whole program, which can sort of be composed of many modules into another through through a particular teleprompter. You could also have higher level, sort of higher order manipulations of your program, where here this thing says, hey, I just bootstrapped a lot of programs. In particular, I could take the top 7. I'd like to have an ensemble program. So this is going to function as a kind of a similar solver that has the same overall signature that we have, but I'd like it to basically run all 7 and pick a majority vote. There's a lot of other things you could, that fit this pattern. So things like, KNN manipulations, where you say, I'd like my program to actually bootstrap demonstrations based on things that are similar to the question I'm trying to answer now. A lot of other sort of possibilities there. So with this same program, the vanilla program, the first one we wrote, we have results here with GPT 3.5 and Llama 213 billion chat. And what you see is that exact same one-liner compiled with the with these one-liner or two-liner prompts, compilers. You can see that you can take a model like Llama Chat, which absolutely sucks at this task if it's done 0 shot, especially if if there aren't human chain of thought that you're giving to the model. So if you're just prompting it with the numbers, to a formidable 39% score with this very basic program that's not even doing a chain of thought. Obviously, if you add a chain of thought, you could get really good results out of GPT 3.5 and Llama 2. And if you add this reflection module that took us like 5 or 6 lines, I forget, and you simply use one of these compilers, you can push Llama 2 to close to 50%, and GPT 3.5 close to 90% on this set. So this was sort of an overview of us building 3 programs of varying complexity. The last one was somewhat complex, and compiling it into really excellent sort of systems by allowing them to self-improve internally through a built-in teleprompter in DSPy. Now you could move on to a number of other tasks. We could take on MultiHop Questions, a task that I like because it sort of helps look at various pieces of this. So these are questions like, which award did Gary Zukav's first book receive? And there are 2 subtasks here, really. One is finding passages from Wikipedia that can help sort of answer this task, and the other is actually generating the answer. So you could build all kinds of models here, but let's say we want to build a program that looks like this, something that can take the original question, ask the language model to generate a search query. So a question might be something like, hey, how many stories are in the castle David Gregory inherited? And this is a question that generally stumps language models. If you go to GPT 3.5, GPT 4, they'll either abstain or they'll give you something silly like David Gregory inherited Castle Gregory, which is kind of a made-up thing. So we'd like the first step to be, hey, language model, please generate a search query for us. So what castle did David Gregory inherit? Something that the retriever could take, something small enough that the retriever could take and actually do a really good job at just identifying that this guy inherited this particular Kinardi castle. Then you can go back to the language model and essentially issue another query. And the language model might say something like, how many stories are in this castle you're talking about, Kinardi Castle? Again, it can be something, or it should be something simple enough for the retriever to immediately find it, such that the language model could holistically take all of this and answer the question. So we're seeing a lot of these workflows, and LlamaIndex has a lot of these workflows where there is kind of back and forth between, or multiple hops, you could say, between the retrieval and the language model. And our goal is to make building arbitrary things of various levels of complexity of this sort as easy as just programming the workflow that you see on the left. So if you are to do this in DSPy, you're going to build a class, and it only has two methods. So in initialization, we just need to declare the components. So this thing has, in fact, three unique components: the red stuff, like generating search queries; the orange stuff, which is the retriever; and the blue one, which is going to generate the answer. So let's actually just do that. So we can have a chain of thought module, or you could have any other type of module here that's going to implement this signature. So this is a signature that's going to take a context and a question, and it's going to generate a query. Notice that this is different from taking a question and outputting an answer. It's a different signature. Then you have the retriever, and let's say it's going to retrieve 3 paragraphs at a time. And then we can have the answer generation. So this is going to take the context that we've gathered so far and a question and generate the final answer. In the forward function here, we can chain them. And again, you're not restricted to chaining in sort of fragile ways or sort of rigid ways. You could write a loop. You could have the loop sort of depend on the particular question that you're trying to solve. For simplicity, let's say we're going to have 2 hops as the diagram on the left shows. So we're going to use our modules. So first, we're going to generate a query. We'll give it the components we have. We're going to take the search query out of it. We're going to take the stuff and append it to the context that we're building. So this is going to retrieve some passages. We're just going to throw them into the context. This is all sort of imperative code. So you could easily sort of inject the print statement here or whatever to inspect what's going on. And you could simply generate the answer at the end and return that as the output of your system. Because this is essentially a DSL, or like a domain-specific language in Python, you are basically free to do all the kinds of things that you would want to do in a pipeline like this, like tracing or inspection, or putting in a debugger on, or using exceptions, loops, recursion. It's basically free-form Python code as long as you follow a few high-level things. So yeah, just some color coding about the stuff on the left and how they map on the right. So under the hood, though, all what we have here is that we're just saying, I'd like a chain of thought behavior with a signature of context, question becomes query. We're not saying how that should be done, but the compiler, given your choice of teleprompter, your choice of metric, and other things, is going to have to map that into something that can actually be executed given your language model. So on the left here, I have, assuming your language model is set to be Llama 2 chat, the 13 billion variant. So that's something you could run locally potentially. Also works with 7 billion parameter models. So it would compile this first step into a prompt like what you have here on the left. And interestingly, it would do that without any labels from your end on what makes for a good search query, or what makes for a good chain of thought for generating a search query, or what makes for good passages with hard negatives for generating this sort of thing. This is all internally bootstrapped in accordance with whatever metrics you're trying to optimize for. This is optimized purely for having generated the correct answer with no other sort of elements. So what does a teleprompter do? I mean, it sounds like it's kind of at this point, it does come across potentially as this main element of doing magic here. So the teleprompter generally does 3 things. It needs to generate candidates, right? So you've seen we've generated these prompts, and so they have different elements or quote unquote parameters that can be learned. The key one really is demonstrations of the behavior that you'd like to see there. So if we have something that generates search queries, you'd like examples of us generating search queries. And maybe I'll try to wrap up after this. So generating good examples of those using the same language model. So this is, if you're using Llama, it's Llama bootstrapping itself. If you're using GPT, it's GPT doing the same. Although you could also do sort of cross-model, essentially teacher student setups pretty easily. The second is parameter optimization. Like, okay, now you have all these potential candidates. How do you select a few that actually work well? And the third is higher order pipeline optimizations. So, hey, I have this program that's pretty linear, but I'd like something that can do backtracking. Like if some assertions fail or something fails, I'd like it to basically go back and retry things in an automatic way. And the DSPy paradigm allows for teleprompters to do this sort of thing, and we're exploring a lot of that. So the question is, like, how does this work in practice? And to basically test that, we have here some results with a few programs. I'm not discussing them here, but you could take a question answering vanilla thing that relies on the model itself. You could build a chain of thought RAG in a like 2-line thing in DSPy. And what you can see is that the few shot version of these is pretty decent. But if you ask the model to bootstrap its own examples, you could potentially get some really decent gains out of them. Agents are another class of things that's highly sort of supported. So you can start with something like React zero shot, which is how it's usually done in like LangChain and other places, because it doesn't know about your tools, doesn't know about your task. If you have human labels, you can add them in, and it does help a decent bit. But if you simply use the compiler, you can generally do it quite a bit better than the human labels will allow you to do. And this is kind of all general purpose here. We don't need to hard code prompts for these approaches. If you use this sort of easy to code multi-hop thing, very basic design, you're able to push these way higher, including with a model as small and local as Llama 2 Chat, and you can certainly do even better than that. Interestingly, you're not limited to prompting. So something as tiny as T5 large, you could probably run it on your phone pretty quickly with 800 unlabeled questions and a few labels, 200 labels in this case. You can get it to score 39% answer exact match and 46% passage recall, which is actually really good. Like this is it's around 10 points better than what you get out of Colbert V2 by itself. And this is mainly leveraging unlabeled questions. So I'll wrap up here. I have some other slides that we can use for questions and whatnot, but the takeaway is don't mess with the weights of your system. Don't mess with the prompts by hand. Define new modules that express the behavior that you want, or define new teleprompters that optimize things in the way that you want. Don't expect, I guess that you guys don't need to hear that, but many other folks do. Don't expect one layer to do all the work. Think about multi-stage pipelines and how you can add depth in your system so that you can sort of solve more complex tasks through these pipelines and programs. And if you do research, or if you care about reproducibility or cost and whatnot, this stuff allows you to use models like T5 large or FLAN or Llama 7 billion or 13 billion, and get really high quality systems by simply through this notion of compiling. And so this stuff is open source. Feel free to check it out. I'll stop here and we can start taking questions where we can also kind of use some of the slides as needed. So I'll turn back to you, Jerry.
Great. Thanks, Omar and Thomas, for the presentation. This is great. This is a super interesting idea, and I'd love to dive in a little bit more. And for those of you who don't know, we actually featured Omar like a few months ago, actually, on DSP at the time. And so now I think the main change is the Y. I was going to ask why you added a Y at the end, but like it seems like one of the main additions is this idea of like compiling optimization, which I'm really excited to dive into. Maybe to start off with like a high-level question is, what are your general takes on like prompt engineering? It seems like you've said like loud and clear that in the first point, like you should abstract away the need to manually tune your prompts. What are your thoughts on whether like prompt engineering should be a thing, maybe part of it, maybe all of it, right? And how will this like evolve over time?
Great question. You might expect me to say it should die and no one should ever do it, but the answer really is there's a lot of interesting kind of developments, research, and I don't mean research only in an academic setting, all the kinds of things you guys are doing and lots of other cool people are doing. It's important to discover new capabilities of models. But once we understand what the capability looks like, I think it should be generalized into a module that can be reused in a well-defined way. So here, chain of thought, someone had to come up with that. The team that discovered it had to come up with it, or program of thought or other things. And I think a lot of that comes through, free form. Not all of it for sure, but some of it comes through interacting with the models in a fairly free form way. And some of that is hard to replace otherwise. Once you understand that particular pattern of behavior, though, it's pretty straightforward to just say, okay, here's what a general purpose task independent module should look like in practice. And I can show you guys how chain of thought sort of is implemented in DSPy. It's actually really simple. Under the hood, that thing should be parameterized such that on any new task that you have, you can simply compile it, optimize it for your data instead of the usual thing. The usual thing is we all like chain of thought. So every time I'm starting a new sort of pipeline, I'll sit down and write a few chains of thought for that particular step. And if you want to sort of be meticulous, you could say, like, for that particular step, for this particular LLM, because what works here is not what works there too well. And this quickly, I think, becomes unmanageable. So you have to compromise somewhere. And we're saying you don't need to compromise. Just build a general purpose module, forget about it. You hit a case where you need more developments, do your due diligence, implement the simple thing. It's extremely easy to do this in DSPy. Like, chain of thought is a line, right? Or program of thought is a line. React is a line. Compile it for your thing. And that gives you, at the very least, a really strong baseline. Based on that, you can write your other prompt and see if you're doing better. And if you are, make it a module. People can then use it for new things, and you can take things from there. So hopefully this sort of helps characterize this. Another element here is what's never going to go away, I believe, is good system design. So what we did here is that we said, like, what's the problem like? Well, we have questions. We'd like to generate search queries. We have those interactions. So that good system design is really key. And all we're saying is, if you think at the higher level of abstraction, where language models can simply sort of be, these devices that you can interact with high-level signatures and with modules, then you can start exploring a much larger space of design, where if things fail, you still need to look at the traces. You still need to understand things, but your first intuition is usually, should I add some internal logic here, or should I kind of create some exception, add some routers, thinking at a high level of architectural design, as opposed to, like, should I maybe fiddle with the last word in the prompt and kind of hope it works on a couple of examples and pretend maybe that's okay. So that's the general picture here.
Makes sense. I guess going along that point, like, I think one of the core components is, assuming you can abstract this away in a module, a core component is the optimization piece. And just talking a little bit more about how that works, like, when you think about, like, compiling a program and you try to optimize, like, the bits, what are the main bits that you can optimize, just very concretely? Is it adding, like, feature-on examples? I see a bit in there about, like, fine-tuning a small LLM as well. What exactly exists, like, at least today, and then also what do you see kind of existing in the future?
Yes, that's a great question. So the real sort of optimization logic exists in two places. One is the predict module, which is kind of like the key core prediction module, and that defines what sort of and anything else that you would add that would play a similar role. That defines what parameters you'd like to optimize. At the moment, the key parameter, and I think this will forever be the key parameter, is demonstrations. So this is a slightly more general thing than few-shot examples. Demonstrations are basically good examples of input and output to the module that you have within the constraints of the signature that you're working with. So if you're generating search queries, it's, hey, here's the question I saw as an input. Here's the chain of thought I generated. Here's the search query I produced. And maybe here are the passages I conditioned on in the meanwhile, whatever other elements, right? Whatever other elements. And the idea here is that you can sort of create a lot of these in an iterative fashion by simply using the logic or the scaffolding of your program. So that's the key parameter. Other parameters we have people sort of explore and sort of will have additional teleprompters for. There are the instructions. There's been a bunch of recent papers on sort of tuning the instructions for models. Usually what's happening there is people are looking at, like, a prompt as the logic. And so they're usually trying to change the last few words mainly before, like, you prompt the model to get the answer. So generally, basically generalizations of chain of thought. But what we're working at the level here is one where you generally have a more complex system with multiple stages, which is what you have in LlamaIndex and in kind of many practical settings. And the interactions between these things are not things for which you have a lot of labels. You don't know a priori what kind of search queries you want to generate, so you can't really optimize this sort of by more standard techniques. And so teleprompters would allow you to do that if you define instructions as one of the parameters there. Another thing is, and this is kind of a special case of thinking about the instruction, is the exact signature to prompt mapping. So you said you want to generate search queries, but maybe the language model knows a better keyword to use for these types that you have. That's another thing that could be automated, although demonstrations generally take most of the burden out of that. You could also have hyperparameters in your logic, like how many passages do I retrieve, or other factor, like what thresholds should I use. These are all things that are not our focus right now, but are pretty trivial to add because the infrastructure around the automatic optimization is there. So you basically have the scaffolding for this stuff. But I'd like to emphasize that demonstrations are the key part, because they allow you to fine-tune models, they allow you to prompt models, they allow you to get really excellent results pretty quickly. So yeah.
Got it. Thanks for the answers. And then the next piece here is like, how do you define the metrics that you optimize for? Do you predefine this? Do you let the users define this? Like, is this some concept of accuracy, cost, latency? Do users define these objectives, or do you do it yourself?
Yes,
I think it's also related. It's related to one of the questions.
It's completely user defined, but we have a lot of built-in things that you could just use if you're doing something fairly standard. Like answer correctness is a common thing, especially in academic benchmarks. They're kind of reusable things, but in practice, what we've seen and what we've built a few times is usually your metric is going to be another DSPy program. So we were doing this task where we had to do data mutation, like we had a specific data format and we wanted to generate something completely different, and it wasn't something we can deterministically check. So we wrote a different DSPy program that does the checking, and then we compiled that on a couple of labels. We just wrote a few things like, here you should say yes, here you should say no. We compiled that, so it was pretty easy to compile because the output of the evaluator is deterministic. It's pretty easy to evaluate. So the metric there was easy. That gives us a program that we can use as a metric, and then we compile the bigger thing with the DSPy metric. So it's completely open-ended. What you're given in your metric is the kind of the output prediction object from your program. That could be like your answer, your query, your other things. And you're given a trace of all the stages. Like, I saw the following chain of thought. Here's what I outputted. Here's the input, here's the output. And you're given whatever labels exist on your end. Maybe that's empty. Maybe you don't have no labels. Or maybe you have the right answer, for example, and you'd like to check that the answer is correct. Maybe you have the right passages and you want to check that you're getting the right passages. And teleprompters will work with any of these to basically hill climb on the space of parameters that you have until it plateaus and it can't optimize your metrics even further. Fairly standard optimization, nothing special there.
So along these lines of time and costs, one of the questions from the audience is, how expensive is this compilation process, both maybe in terms of time and then benchmark ballpark 3.5 turbo dollars, just how much would that cost you?
Yeah, great question. As cheap or as expensive as you'd like it to be. So we've done a lot of compilations that take 20 seconds and are virtually free, especially if you're doing this with a local model teaching itself. I mean, nothing is free, but costs that are sort of pre-paid in some sense, and it takes a few minutes. We've done things where you're going to fine-tune a local model, and for that you're going to ask Llama to annotate a couple thousand examples. And then you're going to train the model on that, so it might take an hour, right? So that's the usual range. I think the longest we've done are things that might take 5 or 6 hours, where we're training flan x large on thousands of generated internally generated data, and what it takes time is you got to go to Llama and bootstrap all these examples and whatnot. But you can run, if you're doing this with GPT 3.5 and you're compiling on a couple dozen examples, couple hundred examples in a large case, you never need more than that. You can expect to pay $10 is a good range, maybe less, $5 to $10 depending on particular details that you can configure. So you have all the control over the settings. But basically, the main setting here is how many trials do you want to conduct? Do you want to try 100 things, which is a lot? Do you just want to try a couple, 4 or 5? and you generally get diminishing returns. So if you'd like to get something very quickly, 4 or 5 trials avoids kind of worst case scenarios and gives you really excellent performance most of the time.
I see. And just to double check my understanding, is this something where like the user specifies the different things that you can do, like to fine tune a language model, to add like few short prompts, like a bunch of different options? Or
is this something the user, I missed
oh, sorry.
the word. Is this something the user what?
Oh, is this something that the user figures out on their own, like manually specifies? Like they specify, hey, go and fine tune an LLM, or go and like figure out like the best few shot prompts, or is it something that you automatically decide for them?
There are many different teleprompters. So there's a teleprompter called Bootstrap Fine Tune, and there you specify, well, I want to fine tune into what? Like I'd like to fine tune into OpenAI's GPT 3.5 fine tuning, or maybe T5 large, T5X large. And the idea is that once you've written your program, what I think a lot of us are realizing in this space is like, hey, maybe I should should I fine tune or should I do RAG? And the answer is like, why should you choose? I mean, it's the same program, just say fine tune with RAG. And you just literally say that, it's one liner, you get a fine tune. Maybe you would like to do prompting instead. So is it something that can be trivially automated by having like a teleprompter that tries different things and gives it back to you? Yes, but I don't think that's the right mode, because that's such an important decision that you want to be at least saying, yes, I want to fine tune, or yes, I'd like to prompt.
Makes sense.
But the steps of fine tuning are not something you're going to do. You just say, here's a program, here is my sort of metric, do a good job.
Right. Yeah, that makes a lot of sense. So going back to the question in the audience, I think one question is how much like does DSPy? So I think in the experiment, like you demonstrate a lot of like performance gains. Can like this idea of compilation actually reduce like latency or time compared to like vanilla QA pipeline they could implement in LlamaIndex, LangChain, and other frameworks?
Great question. We are not focused on like systems level optimizations, although there are people at Stanford who might have interesting things there to add to the framework. But that's not sort of the core focus. The main way we can cut costs here is 2 things. We can compile simple pipelines to really good quality. Like you could do just basic RAG and without multiple steps. And when it's bootstrapped, when it's compiled, it does better than I think it does better in some cases than the multi-hop thing, without all of the compilation. Obviously, if you compile, you could do even better. But the other element of this is that we can usually get things working really well with very small models. So the pipeline itself has all the steps. We're not making any steps faster. It's just that you don't have to do like GPT-4 for almost anything really, because if you compile it with Llama, or 13 billion, or distill that, into T5, you can get really excellent performance as long as you understand your task. Like meaning if your task is very opaque, like you just have an input and you have no clue what to do with it, obviously no free lunch, right? But if you have a pipeline that you understand well, you can get really excellent performance from very small models. So that's the main way latency improvements come in.
I see. I feel like given that you just have let the user define a bunch of metrics, like just from a general optimization problem, if you let them define like, I don't know, like latency or time as like a metric to optimize for, you could hypothetically just go in and pick some combination of techniques that.
So it's easy to optimize for. It's easy to optimize for proxies to that. Like I'd like my prompt to be under 1,000 tokens, assuming that affects your cost, which it does. That's easy to do. Actual latency is hard because usually these things are highly parallelized. Like when you say compile, it's not going to do one thing at a time. It's going to launch a bunch of different things at once. So it's going to be actually fairly non-trivial to think about how to get like those profiling elements of latency.
Gotcha. How much does this is a question from the audience. How do you have plans to integrate the teleprompter, like the compilation, with kind of like other evaluation frameworks, things going on? Like if the idea is just so that users can define like arbitrary metrics, is there a way for them to kind of integrate with other, there's a lot of like eval toolkits these days for LLMs, and to somehow like pipe the results and create that integration?
Something like what?
Sorry, there's a lot of eval toolkits these days for LLMs. So is there a way to kind of like integrate DSPy with some sort of like downstream evaluation provider so that would provide signal back into what to optimize for?
So DSPy is pretty modular and small. It's not meant to be, an overarching thing that you have to use alone. It's generally it's plug and play. As long as you write your core pipeline logic there. You can do whatever you want for instrumentation or for bigger things. And if you go through the frequently asked questions on the page, we actually explicitly say like it would be cool for people to build frameworks on top of this. Our mental model for this is PyTorch. There's lots of frameworks built on top of PyTorch, either for lower level things like PyTorch Lightning and whatnot. But I think I usually think of like Hugging Face transformers, where you have this huge ecosystem. You can do instrumentation with things like also TensorBoard and other stuff like that. As long as I think this is something good for all of us. As long as your inputs or outputs are clean, we're gonna give you strings at the end of the day. Like the output is just a data structure. So as long as the other tool that you're working with has good interfaces, it's gonna be pretty trivial to integrate it. We're not making any like weird decisions that make integrations hard. Tracing is easy, integrations are easy. Are we gonna have anything built in per se? Not really on the roadmap for the near future. Inside of DSPy.
And I think one of the other questions from the audience, this is just going through our list, is in terms of using DSPy, and if I had to think intuitively about this idea of like compiling something, does it lead to better kind of like custom data domain performance? Like if you have a bunch of like your own unstructured data and you want to perform queries over that data, does it lead to improvement, and what parts of that optimization process lead to improvement? Is it the bootstrapping example, like the fine tuning, that type of stuff?
Great. So one of the kind of examples of this is we were trying to adapt. We were running React in our experiments, and React was sort of, it's a fantastic idea. It's really a great, obviously highly impactful project. It's defined in terms of a workflow, but in practice, there is a particular set of tools that they use to do question answering. And so their prompts wouldn't actually directly work with Colbert V2 because they were assuming you had a Wikipedia API. So the question is like, how do I get React to work with Colbert? And we can sit down and try to like come up with different prompts that would work well for Colbert, and then we get some passages that are actually Colbert-like, and we could think about that. But with the actual DSPy of implementation of React, we were just like, okay, here's the tool, here's the actual tool I have, here's some metric that I want you to optimize for, here are some questions, and here are their answers. Like, please bootstrap good few shot examples for React for me. And where does the adaptation come from? Well, it comes from the fact that when it's bootstrapping those examples, they're coming from your domain. It's not coming up with like, it's not someone hard coded for a different domain. It's working with your actual data. And when it's optimizing the metric, it's optimizing it again over your data. So no magic involved. It's simply the fact that if you want to climb hill A, you climb hill A. If you want to climb hill B, you climb hill B. And obviously there's too many hills to climb. So if you can automate it, that would be fabulous. And we're not, by the way, making any claims in DSPy that we have the absolute best teleprompter or the best compiling strategy. This is completely modular. So you can easily come up tomorrow and say, hey, you're compiling in this way and it's kind of inefficient, or, it's not great for my type of application. Add a new compiling strategy. It's one more module, like it could be 20 lines. We have great sort of contributors, working with us here, and people within a few weeks of starting, they can build a lot of these sorts of modules pretty quickly. So add a new module for your optimization thing. We can merge it in if you like, or you could have it externally if you want, and people can apply it to all kinds of problems immediately. So we're making claims about the abstraction that are strong, but we're not actually making a lot of claims about like the modules that are there. The modules that are there are simple. You could do better.
Mm-hmm. Sweet. And then the next question, there's a question from the audience, but I figured it's also a good refresher just to, because I think I have some basic understanding of DSP and DSPy from last time as well. But like when you say just this idea of like few shot examples or like prompt candidates, like maybe just like very concretely, what exactly do you mean? And when you talk about like compilation, like what exactly are you optimizing there? And how does that actually help prompt engineering?
Great. So let's get back to the basics. You've defined your program in DSPy. For that, what you did was you defined two methods, right? One is initialization. And initialization, what you did was that you declared a few modules with signatures. So you said, I'd like to have a chain of thought that takes A and gives me B, maybe takes questions and gives me queries, and some other ones. Let's say it's just one. Or actually maybe a couple would be good, so that there's some pipeline that's happening. So let's say you have two of these and maybe some other tools. So it calls out to a SQL database or calls out to a retriever, whatever, or runs code execution or whatever it is. We have a sandbox. So the other part that you're going to define is your forward function, which is going to have the interactions between these things. Now, with these two, if we have any inputs, like let's say the question that you want to ask, or it could be other, the document you want to summarize, whatever input you have, we can easily run it through your code, right? Because it's just a function call. Now, the only part that's not well defined yet in this function call is what should happen when a module gets called with some inputs. So you have a module that's a chain of thought module. You give it a question, it's supposed to give you a query. What should actually happen there? You could start deterministically. You could say, like, it's pretty easy to take your signature and map it into a zero-shot prompt for your default language model, maybe GPT 3.5 or Llama. Once I have that, I can run through the rest of your pipeline. So every time there's a language model, I'll make a zero-shot call. Pretty trivial, nothing interesting there, to GPT 3.5 that just tells it, hey, I have the signature, I have those values, please help. According to whatever the module adds in terms of structure. So chain of thought will say, hey, when you're doing this, just think step by step. So once you have that trace, you now have a lot more information about the pipeline, because you know what examples work and what examples don't work. And for examples that work, you know what exact traces through all the stages had to be created. And once you have those, you can kind of go back to the module itself and tell it, hey, those examples were good for this particular module, like remember them for the future. And you can generate a lot of these, keep the good ones, maybe keep the bad ones if you want to do some kind of let's say preference training, but maybe you can just throw them away if you don't want to do that. So the current teleprompters will actually just throw them away. And once you have those, you could do an optimization problem where your goal is maximize the metric, subject to the fact, the structure of the program, where the space of optimization is basically finding good prompts from the demonstrations you collected, or fine-tuning good models from the demonstrations you collected, or whatever it is. So hopefully this kind of gives you a big picture of what are the moving parts here.
Right. And just to be very concrete, the idea of actually adding few-shot examples generally tends to improve the capabilities of LLM to actually output the correct decision, right, as opposed to zero-shot prompting. And to be clear, I think a lot of the prompts, like the React prompt and LlamaIndex line chain, is zero-shot. It's just oh, please, you're an instructor that does this and this, and please output the next query. I think there's some fixed few-shot examples in the React prompt in both frameworks, but I think the idea here is it can also be dynamic depending on the type of query, right, and the training set that you upload.
So the issue with few-shot in general is you can do few-shot predetermined if you know what the application is. But let's say you want React work. I mean, thinking of LangChain, for example, they have this excellent. They had it very early, zero-shot React agent where it can take any tools and it just works. And that's a really cool abstraction. The part that it's missing, and that has the answer in DSPy, is that when you give React tools and you compile it, it learns to use your tools because it can try them out, see what works, what doesn't, and basically bootstrap from there. And one thing that we've actually seen works really well in the paper is you can actually take this React that you compiled and use it as a teacher for an even better compiler, in 2 more lines of code, and get a really good React system that can outperform the human written demonstrations.
Sweet. Yep, makes a lot of sense. The last question I was going to ask, and this would be just the question to close out the webinar as we're nearing the hour, is as you kind of think about the future, one part of this question is what is the future vision for DSPy? And then the next part is, in a world where everyone uses DSPy tools, what happens to the space of LLM ops? What tools become more or less important? And maybe this is a pretty general question, but I'm curious to get your take. Everything from prompt versioning, tracking, monitoring, all the way to kind of this optimization piece. Does that become a component? You might need some cloud managed service to help run just optimizations, compilations, that type of stuff.
That's a great question. So what I'd say is our vision is that this really becomes the PyTorch of the space of programming with foundation models. And what I mean by that is, PyTorch was obviously not the first neural network framework. So there's a lot of sort of special things here that I don't mean. But what I mean by that is a highly accessible framework targeting kind of really more research and development things where you're building new things and exploring new ground for the first time. And the idea is that when you're trying to build applications, you sort of have higher level abstractions where you don't really sort of have to write new models yourself or new programs yourself. You can simply use something off the shelf. That off the shelf thing is internally going to be really powerful because it's internally using a compiler that can adapt things using DSPy to whoever is using it, to the data of the users using it. So the idea is that we'll keep adding modules. We have a lot of teleprompters sort of on the way that are sort of richer in terms of the families of optimization algorithms they can apply. We're gonna add more and more sort of these programs. But one thing we're not going to do, for example, is start adding like here long lists of things that are important for application development. We're not going to add like integrations to all kinds of tools. We want this to be very minimalistic and modular. And we hope that higher level frameworks like LlamaIndex and others, I mean, I love the abstractions that exist in LlamaIndex in particular, and the way you guys are sort of always updating you support a lot of the richest kind of multi-stage pipelines. So our hope is that sort of adoption will happen at the level of the stack here, where programs can be done in this super modular, compilable abstraction, and higher level things can be exposed to users who don't want to mess with the internals too much. As for LLM ops, I mean, versioning is still super important. Tracing is still super important. At the end of the day, there is an actual prompt somewhere that's being produced. You'd like to look at it because maybe things are not working and you want to debug it. That's not going anywhere. But I think as you're alluding to, some shifts might start to happen in terms of what matters and what doesn't. And I think that might be a significant redesign, because I think we're changing a lot of the focus from prompt engineering being this really new complex thing into saying, hey, it's just an optimization problem. And we kind of have a lot of rich sort of understanding of how to deal with training and optimization problems. Can I track my metric over time, or can I, which doesn't really exist for prompt engineering right now because you're doing it manually. But A/B tests and things like that will obviously still exist. And versioning of your program versions, like, hey, I changed the loop here or something, is still obviously super important.
Awesome. Well, Omar and Thomas, thanks so much for your time. It was a great session, same as last time, and thanks to the audience for joining in. And the recording will be up, and there's a lot of really interesting insights covered here. So thank you all, and have a great weekend.
Thank you, Jerry. Thank you, everyone, for listening.